Good evening, good morning, and good afternoon, everyone. Hi, welcome to the Youth Talks organized by ICANX today. So we have three prestigious speakers today from different continents, and I proudly present the talk to you today with the help by Liz Chang here. And we're gonna start the talk now, and I would like to introduce myself first a little bit here. So my name is Vibhu Piyavatana Mehta. I'm a professor in biomedical engineering at King Mongkut Institute of Technology, Lat Krabang, Bangkok, Thailand. If you ever come to visit Thailand, please come and stop by and say hi to me. Yeah. Today, we have three distinguished professors here who would like to present you the latest work, and they are all ladies, in fact. So the first one, will be Dr. Sasitorn Srisawadi. Okay. And the second one will be Zhao, Professor Zhao. And the third one will be Judith Su. So I would like to introduce the first speaker of the session today. Her name is Dr. Sasitorn Srisawadi. She's a very good friend of mine from Thailand, actually. She's the team leaders at the National Materials Technology Center, one of the research centers in National Science and Technology Development Agency, Thailand. She earned a degree in industrial engineering from Chulalongkorn University, and she won many prestigious awards. And she actually graduated from North Carolina State University, where she worked in additive manufacture and rapid prototyping. And she actually would like to present you the topic on printing. And with no further ado, I would like to actually give the floor to her.
Thank you, Vibhu, for the very kind introduction. And also thank you, ICANX, for having me here in this youth talk. I'm very excited to be here, and I heard that this is going to be one of the inspirations for the younger generation to get into the career in science. My talk is going to be about the 3D printed functional materials and the potential applications. So I like to start with a little bit about my background. So I actually have a background in engineering. I study and I did my research when I was doing my master and my PhD based on the technology of the additive manufacturing. And actually, when I was a student, which is a very long time ago, we don't really call that technology 3D printing or additive manufacturing. We called it rapid prototyping because back in the days, you only use that technology to produce the prototype. But as of right now, the technology has developed so much and it evolved and it got more mature. And that's why people started to use the technology to print the production part, like the actual functioning part, instead of just the prototype. So that's how long ago when I was still a student. And so right now, my research activities still focus on the technology of the additive manufacturing that includes the natural rubber printing, which I will be giving you more details in my talk today, and also the additive manufacturing of the metal matrix composite, or MMC. And on top of that, I just want to tell you all that I'm also a gym addict. So I go to the gym a lot. I work out a lot in order to, release my stress that I got from the work. So if anyone who feels really stressful with your work right now, I really suggest you that you should go work out, and that's good for your health, physical health, and also mental health. That will be all for about myself. So next, I just want to introduce my country just a little bit. I'm pretty sure that most of you know Thailand already, and we are famous, and I'm proud of how we're famous for the temple that we have, the beautiful temples. But do you know how many temples do we have in Thailand in total? So we have a lot of temples, and actually there are over 42,000 temples in Thailand. That's a lot compared to how many provinces that we have. So that's one very interesting fact about Thailand. And before I will go further into my talk, I just want to show you where Thailand is. It's actually in the Southeast Asia. It's next to Laos and Cambodia and Myanmar and Malaysia, and with a total size of 500,000 square kilometers. Do you know that 39,000 square kilometers that of the area in Thailand? What do we do with that area? That's about 7% of the total area of the country. In that 35,000 square kilometers, we plant rubber, natural rubber. So we grow trees, and there's a lot of farmers who investing their time and their money into making the natural rubber within that 7% of the land in Thailand. And if you come closer and then look at those farmer or look at those natural rubber cultivation in Thailand, you'll find out that that's about 1.7 million households in Thailand. That's a lot of people included in that household. And they actually rely very heavily on the fluctuation, on the unfortunate fluctuation of the rubber price in Thailand. So it means that their income, their children tuition, whatever happen for the expenses in their household, it depends a lot on how the rubber price are during that time. Sometimes it's very high, so that's very fortunate for them. But sometimes it becomes very low when the demand is lower and there's too many supply. And if you want to ask me, so what is it like in a day for those rubber farmers? This is what it's like in their day. So they will start their morning very, very early in maybe 3 or 4 o'clock in the morning. They will go out to their rubber plant area, and then they cut the outer side of the tree in order to get that milky liquid out. And then they will put a small bowl right underneath where you cut the tree, so that you can have that liquid drip by drop into the bowl. And maybe a couple hours later, they will pick up the bowl one by one. So there's one bowl for each tree. They'll pick up the bowl, and then they will pour that liquid together in a bigger container. And then they will start a process of making the rubber sheet, which is shown on the right here. The problem is when they sell their product as a raw material for other industrial products, for example, the rubber tires or other sealing parts. When you sell that for the raw material of those products, the price is very low. So when I came back from the United States after I got my PhD with all my excitement of using the 3D printing technology, I actually got to talk to some of these rubber farmers. And then I thought, that's one way that we can make the price of the rubber more stable or even higher than what it is right now. And I think that one way is if we can make that natural rubber printable, and then we can make a premium product, or we can make a very high value product, and then we can export it to other countries. So that will increase their income. That will make their economic status more stable. And of course, they can afford the tuition for their children. So that's what I had in mind a couple of years back. And then I went to the lab, and then I keep doing and keep repeating my experiment. And that's how I and my group were the first group in the world to be able to make natural rubber 3D printable. So with this technology, we had it patent under a lot of domestic and international patents. And it was very successful, and we were very excited about it. So what we did was we made the two parts that you see on the left here. The laser pointer. So these two white parts, these are 100% rubber, natural rubber. It's very flexible. You can stretch it up to 7 times of the original length and it doesn't break. So so we were very excited, but then the problem is, what do we do with these parts? What do we do with this printed rubber? And that's when we thought we have to provide more function to this material, make it a functional material. So that's when these two products came out, the black ones. If you look at these samples, they are black, but they're still natural rubber. And that's because we included something else to give it more function, which I will be telling you in a little bit in the next couple more slides. So with this technology, how did we do that? We actually have the same design principle with the stereolithography technology, but we twist it just a little bit. So basically, you will start with a liquid natural rubber in a vat or in a bath, and then I will have the laser head on the top that would scan onto the surface of the natural rubber. And that's how each layer is formed, one by one by one on top of each other. And then you will have a completed three-dimensional part out of this technology. With this, how did we do it? The trick is that most people thought that in order to make the natural rubber solidify, you have to put some chemicals into the natural rubber latex, and then you need to give it pressure, higher temperature, and then it will start to have the cross-linking bonds between the rubber chains, and that's what we call the vulcanization process. And at the same time that they will start cross-linking, the water needs to be removed from the system. So this is a very conventional way of how you produce a natural rubber product out of the latex. But that's another way that we can do it. And actually, that was the way of how we made it printable. So instead of vulcanizing or cross-linking and removing water, we vulcanize, but we still keep the water inside. So right now you have the polymer that's already cross-linked, that's already vulcanized, but it is still floating like a colloid in water. So that's actually half, is 50% water, 50% rubber. And then I put that in the 3D printer, expose it with the laser, and evaporate the water out. So that will leave a layer that was exposed to laser and without water. And it is actually a solidified natural rubber. So that's the process that I kept doing one by one on top of each other. And each of the layers I made is only 150 microns. So this process gives you a very fine details, a very small feature for the printed part. So when we made this possible, we again very excited about that. And we tested for the mechanical properties. And we found out that when you compare the cast sample and the one from 3D printing, the mechanical properties are about similar. Maybe like 10,000 of the printed part is a little bit lower, and that's because it was exposed to the heat from the laser. But still, the elongation at break or how much it could be stretched before it break is still very high. It's about 700% and up. So this is a very impressive result of the printed part when you compare to the conventional parts. So with this, it opens the opportunities to a lot more opportunities, a lot more doors is open for this technology. And there was one door that we chose to go for is to give it another function, which is to make it conductive. And in order to do so, we just need to mix more conductive filler into the natural rubber latex before it was printed. So you have the whole lot of choices for the conductive fillers. It could be the metal-based nanocomposites. It could be the carbon-based material, for example, the carbon black or the carbon nanotube, graphene, or even graphite fiber. So there's so many options for us out there, and all of them looks very excited, right? Because I'm pretty sure you've heard that silver nanoparticles or copper nanoparticles, it will give you an antibacterial activities to the material. But still, if you choose the carbon nanotube, it will increase the conductivity very high because of its excellent conductivity. And for my case, so we were thinking, what should we choose for our material system? So we all know that natural rubber latex is very cheap, but we want to make the profit for the domestic product, right? So I think we should go with something that's a little bit cheaper on the cheaper end. So that's carbon black. But the challenge is that it's really hard to mix the carbon black with the natural rubber latex because it is water based. And if you have been exposed to the carbon black before, it's oil based. So these different polarities make it really hard to be mixed together. You just need to choose the right surfactants. You just need to choose the right dispersant and also the mixing process. So it's really complicated and challenging. So we found one way that makes things easier is that we can modify the surface of the conductive filler so that we can have the filler that's compatible with our matrix or with the natural ability. So what we could do is to make a very thin layer in the size of the nanoscale of another type of polymer to cover the surface of the carbon black. And then you end up with a carbon black or the carbon nanotube that's very compatible or is very easy to mix with the natural rubber latex. And when you have a very good mixture, it means that your conductive filler will be dispersed very well in your system. It floats around. And when you make a sample that you want it to be conductive, you can imagine that the electron will be able to travel very easy on your sample. And that's because you already created a very good road or a very good network for the electrons. And that's the conductive network that we produce in our system. The picture on the top is actually the TEM images. So the one on the left is the natural rubber itself without any fillers, no carbon black, no carbon nanotube. So you can see that it looks like a sphere, a lot of sphere or like a pack of balls in your system. And when you included the conductive carbon particle into your system, it's shown as those little black dots here that it created a conductive network around the sphere. So the sphere is actually the natural rubber particles, and then you could see that the carbon black will form like the outer surface of the sphere, and then it connects to each other. So with this in mind, imagine that you have this material that have the rod to connect together, and then you have the electron that will be able to travel. What we could do with that material based on this fundamental, imagine if you look at the picture in the bottom. So picture A is actually the original status of your material. So this is how you have the black ones are the conductive fillers that are connected, make it a very good network for the electron to travel. And then in the picture B, that's when you started to stretch, or that's when you make the network further away from each other. Imagine if you go travel and then there's less roads or highways out there, then it's harder for you to travel. So that's the same for the electrons. When it's harder to travel, and then it will end up with different signals or different electrical signals. For example, the resistivity or the resistance would change, and you can detect it by measure the voltage or measure the current or measure the resistance itself. So with the fundamental of how you wanna make the network less dense so that you can detect the signal of your material, we made it into a strain sensor or a strain gauge. So in the picture on the left, that's actually our sample. This black one is our sample. And then we clamp it in between two grippers, and we're slowly pulling it apart. And when you stretch your sample to be longer, longer, and longer, you will see that there's a change in the resistance as plotted in the graph in the middle here. So at the very beginning, you can see that the slope is not very steep. That's because the network is still very dense overall. So maybe some part of the network was broken, but still there's a remaining almost of the network that still remains connected. So that's a very slight change of the resistivity. And then once you stretch it even longer, up to 150% of the length, you started to see a higher or steeper line of the change of the resistance. And yeah, even higher if you keep stretching it up to 300%. The change is even steeper. So this is a very good demonstration or a very good evidence of how we can develop this material further to make it a strain sensor or a strain gauge or something that's related to the strain sensing application. But before we do that, we just need to make sure that our material is reliable enough under the given sensitivity. So we also did a lot of tests. So this include up to 500 cycles of the same stretching, up to 100% strain. So imagine if you have a 5 centimeter long sample, and then you stretch it to 10, and then you go back to 5, and then you stretch it to 10. So you keep doing that for 500 times. And based on the result that we have, I'm very happy with it because it shows a very reliable and robust cycle. So under the same fundamental of how you could stretch your sample to be longer, and then it gives you a different electrical signal, I came back to my team and then we're thinking, is there any other sensing activity that we could get based on the same material? Is there any other function that we can give to it? Because of course, it's very good to have a sample that's flexible and conductive. But then the most important is that the applications that you want to use with that. So strain sensing is one, and we already proved that it's feasible. And actually right now, we are doing a demonstration of putting this conductive rubber on a wearable textile or like a stretchy shirt so that it could detect the movement of your body. For example, if you were sitting and on your computer and you were like crouching and bending over so that you can read better on your computer, it could detect, if you put the sensor in the back of your shirt, then it could detect the stretching of your shirt forward, and then it could tell that, okay, you're not sitting in the right position, your posture is not right, you need to stretch your back and then sit upright. So we are doing that demonstration with the textile right now that I'm talking, because I just talked to my junior colleague today, and it has a very promising result. So I hope that maybe next time or in my next talk, I will be able to share more results with you. And that should be one of the big steps for this material to actually enter the world of application, and then it will give just the very tangible benefit. Yeah, so on top of that, so strength sensing is one thing. We made it possible. What would be other things that we can do with the conductive rubber? This is what we did. We used the same material, but this time it can sense gas. If you look at the plot here, how we put this material to be exposed to toluene, to the toluene vapor, and then we bring it back to the air atmosphere, and then we put it back to the toluene vapor, and that's how we have a cycle of the change of the resistance as shown here. But there's still a challenge for that, because if you look at the blue one, it is actually the one with the less conductive fillers. It gives you a very good sensitivity, because if you see that it jumps very high, there's a big change in the resistance, but it's not very consistent. Because if you see that, like, the first cycle is very low, but then at the fourth cycle, the change is very high. While if you look at the orange line, orange plot here, it gives you a more consistent change of resistivity. Even though the first cycle is a little bit low, and that's because the material is still not saturated with how it's falling. And that's because if you look at the mechanism of how it changed the electrical resistivity based on its exposure to the gas. It is because toluene is a solvent for the natural rubber. So when the natural rubber, or the brown big sphere here, when it was exposed to the solvent that they don't like, they got swollen. And when the sphere got bigger and being pulled apart, and that's how the conductive filler also become very further from each other, and then the resistivity will change. So that's one way. That's another way that we can use the conductive rubber to give it another function in addition to the strength sensing. Now it also can sense gas in different ways. So with this purpose, at the end, I just want to produce it into some other products. For example, the one on the left here is the smart packaging. Imagine if you buy banana from the supermarket, or if you buy milk or meat, it usually comes with an expiration date that's printed on the package, right? And that date is just how they estimated the expiration of the product. It's not the actual expiration date. So most of the time, people end up throwing away their food because they thought it was expired based on what is printed on the package. And globally, we end up with a lot of food waste based on that principle. So imagine if we have the package that would just tell you right now that, okay, they sense this type of gas in the package, and it means that it's about to go bad. You need to throw it away. So that's the right time that you should throw away your food, not before that, not based on the printed expiration date that's on your package. So that's one of the applications that it will be a very good use of how the rubber can sense different types of gas. And also for the strength sensor, or with a combination of the strength sensing and gas sensing, you can make that into a robotic skin or a soft gripper that can sense touching. It can also sense different gas or toxic gas that might be produced in the working area, that might be toxic, that might be harmful for humans. So with this all together, we just hope that the finding that we found in the lab work, the finding that was based on the science and technology, will actually give a brighter day for the rubber cultivation and for the rubber farmers, so that their children will have a better education based on their stable income. So that will be my talk. And if we have any, I'm very welcome to do that, or we can just do it at the end of Judith and Finn's talk too. So thank you very much.
All right. Thank you. Thank you, Professor Sasitorn, on very interesting talk on the natural rubber, and actually made really nice conductive material based on the natural rubber, which are pretty abundant in Thailand here. I'm very proud of her, actually. She's a good friend of mine. So I'd like to introduce the next speaker. Her name is Professor Zhao. She's an associate professor at the Department of Biomedical Engineering at Hong Kong Polytechnic Technic University, or PolyU. Okay, her research interested in transitional regenerative medicine, where she integrates multidisciplinary approaches, including material science and cell biology, engineering, and medicine, to modulate cells' microenvironments. She has won many prestigious awards that I could name off. Okay, and she's currently a founding member or editor of the Engineering Regeneration Associate Editor of the Biodesk, and guest editor of the 11 other journals as well. So with no further ado, I'd like to give the floor to Professor Zhao Xin. Thank you.
Yeah, hello, can you hear me? Hello, can you hear me? Yes, you can. Okay, great. So first of all, I would like to thank Professor Zhang to invite me to give a talk to you. And I think it's very good opportunity to promote more people to do the science and also engineering. So today I'm going to talk about is the photocrosslinkable polymers for tissue regeneration. So this is the red building is the PolyU. So this is typical red building of the Hong Kong Polytechnic University. And today the polymer I'm going to talk about is one of the research interests in my lab. So my lab is mainly focused on three areas. One thing is like we synthesize different materials. So based on the properties we need, for example, if we want to use some materials to regenerate bone, so we synthesize the stiff materials. And if we want to regenerate some tissues, like for example to regenerate skin, so we synthesize some softer materials. And also we make the materials into different formats. For example, microspheres, nanofibers, intractable, and also the 3D printed scaffolds. And also we apply these materials into different applications, for example, bone, tendon, skin. So today we are going to talk about is the photocrosslinkable polymers. So so here is the principles of how the photocrosslinkable polymers they work. So here we have the monomer, and these golden dots, those are the crosslinkers. So upon light exposure, so these monomers they can join together, and we can form these 3D these polymer network. And by controlling these cross-linking density, so we can control the mechanical properties and also the degradation properties of the material, the scaffolds. And the reason why we actually want to synthesize and use these photocrosslinkable materials. So one thing is because initially those monomers, they are liquid. So in this case, we can actually take advantage of these things. So what we can do is like, for example, by 3D printing, so materials can be they squeeze out from the needle, and then we can print them. And then while we print them, we use the light to solidify them, to crosslink them. And then we can make these three-dimensional scaffolds. And also, for example, if we have the fine patterns, we can just pour the monomers, the liquid monomers, onto the fine patterns. And upon the UV exposure, or light exposure, we can solidify the materials. And then when we peel off them from those kind of fine patterns, we can have the nicely fine patterns on top of the materials as well. So we have nowadays we have many these synthetic polymers which are photocrosslinkable, and also we can make the natural polymers photocrosslinkable as well. So today we are going to talk about one of the synthetic photocross-linkable synthesized by my lab, and then we are going to talk about how we can use this kind of photocross-linkable polymer. So I'm going to talk about the four different applications using those photocross-linkable polymer. So one thing, the first thing we are going to talk about is we use the photocross-linkable polymers for 3D printing, and then we print these 3D scaffolds for bone regeneration. And we know that why we want to use the 3D printing is because we can squeeze the materials out, and then by layer, and then we can form these three-dimensional scaffolds. And the problem is that if we want to squeeze the materials out, we need to make them liquid. So either how we can make these materials liquid, we either use a high temperature to melt the materials, or we use the organic solvent to dissolve the materials. Or the problem is that if we're using these, so when we're using the high temperature or when we're using the organic solvent, this will make the materials not able to load the bioactive molecules. So that's why we want to use the photocross-linkable monomers. So in this case, the bioactive molecules can be loaded into the photocross-linkable monomers and then squeeze out, and we print layer by layer, and then we can form these three-dimensional scaffolds. So this slide summarizes the current photocross-linkable polymers. So for example, we have the methyl-acrylated alginate or gelatin methyl-acryloid. So these materials, they are hydrogel. So they have very good biocompatibility, but their mechanical properties is not very good. And also we have the synthetic polymers, like what we often use, for example, the polyhema and also polymethyl-acrylate. So these materials, they have, so once they become this from liquid to solid, they have really high mechanical properties. The problem is that they cannot degrade. And also when they are cross-linking, they regenerate a lot of heat. So in this case, so this heat will also compromise the loaded bioactive molecules. And also we have the polymer plus the ceramics. The reason the normally used ceramics is hydroxy apatite. So because they have similar chemical structure to the natural bone. The problem is that the hydroxy apatite nanoparticles, they might have these kind of, because particles are very tiny, they might aggregate. And also their interaction with the ceramic particles and the polymer is not very good. And this will also compromise the mechanical properties. So in this case, we want to develop a photocross-linkable and 3D printable composite materials with excellent mechanical, biological, and also biomolecule releasing properties. So here is the materials. So this is the materials we are using, and the following projects will also be based on these materials. So for this material, we have the propylene glycol. So this is to make the polymer injectable. And also we have the lactide to make the polymer degradable, and methyl-acrylate to make the polymer photocross-linkable. And also for the inorganic phase, we have the C1C capped hydroxyapatite nanoparticles. So these nanoparticles, they can cross-link with themselves, and they can also cross-link with the polymer. So these will increase their mechanical properties, and also they can modulate the rheology behavior of the composites, so they can be easier for the 3D printing. And also when they degrade, they can buffer the acidic product during the polymer degradation. And also by controlling the M and N of this polymer, and also the ratio of the polymer and the hydroxyapatite, and also how much C1C are kept on top of the hydroxyapatite nanoparticles, we can control the mechanical properties of the materials. So also this is showing you why we actually want want the hydroxyapatite nanoparticles have these C1C brushes. So one thing is because they can cross-link with themselves, and they can also cross-link with the polymer. So these will form these organic inorganic network. These will increase the mechanical properties. Oh, here are just some data. So these are the data to prove that we have successfully synthesized the polymer. And this is some data to prove that we have successfully synthesized the hairy hydroxyapatite. And we can see that, so we calculate that. So on each hydroxyapatite nanoparticles, we can put about 700 to 800 hair. This is something very important. So these HA means the naked hydroxyapatite nanoparticles, and these HAMA means the C1C capped hydroxyapatite nanoparticles. So we can see that when we suspend them in the organic solvents, and after 12 hours, so due to the presence of the C1C brushes, so because they increase the interaction between the nanoparticles, so the particles, they won't aggregate and sediment to the bottom of the organic solvents. What if we use the UV to cross-link the materials? We can see that the hairy hydroxyapatite nanoparticles, they will cross-link with each other, become bigger particles, and then sediment to the bottom of the organic solvents. So this means that the hair, C1C hair, they can enhance the colloidal stability of the hydroxyapatite nanoparticles, and also they can cross-link with each other under the UV. And also we examine the effect to see that if the incorporation of the hydroxy nanoparticles will affect the polymer polarization. And we can see that all composites, they can be cross-linked within 140 seconds. And also we can see that while changing the ratio of the HA and also the polymer, and also the hair, how much hair we add to the hydroxyapatite nanoparticles, and also the MNN, as I mentioned, so we can control the cross-linking density of the composite, and then we can actually robustly control the mechanical properties of the polymer, so from 40 to about 400 megapascal. And this is something very important. So we can see that, so when we cross-link the conventional HEMA, so the temperature will increase to about 70 to 80 degrees C. So this means that if we want to encapsulate some very active bioactive molecules, so these will actually kill these bioactive molecules. But when our polymer, they cross-link, the temperature will only go up to about 36 degrees. So in this case, that means that our materials, they can actually preserve these bioactive molecules. And then we also encapsulate the bone morphogenic protein. So because it's a FDA approved a growth factor for bone regeneration. So we can see that our polymer, they can encapsulate and also the long-term release of the bioactive molecules. And we also see that, so we use the different concentration of the hydroxyapatite nanoparticles to polymer, and then we can adjust the viscosity. So, and then we find that we can actually print these 3D structures with high resolution. So nowadays we are actually using another 3D printing methods called the LP. So now we can actually print this resolution to about 100 micron. And also we can examine the degradation of the composite materials. And we can also see that when the composite degrade, they can maintain the pH around pH 6. This is like advantageous, is because if this means that we have reduced inflammation. So if we want to implant these materials in vivo, so we actually want the less inflammation. And then we examine the biocompatibility of the materials. So these green cells means the cells are alive, and these red dots means the dead cells. So we can see that most of the cells on top of the composite, they are living cells. And also we can see that the cells can spread on top of the materials. And also we can see that with time, the number of the DNA means that the number of the cells increase. That means that the composite materials, they can support the survival, adhesion, and also proliferation of the materials. And also we examine these in vitro osteogenesis using the ALP's alkaline phosphatase. So this is the early marker of osteogenesis. So we can also see that our composite material, they can enhance the in vitro osteogenesis. And we use another marker, it's called alizarin red. So these things, the calcium deposit, so which the color is red. We can also see that our composite, they can actually enhance the mineralization, so the calcium deposition of the mesenchymal stem cells. So after we prove that our materials, they are biocompatible and they can also support the in vitro osteogenesis, we implant these scaffolds into the rabbit female condyle defect. So we can see from these images, so this green means our scaffolds, and this red color means the newly regenerated bone. And we can see that our composite with the bone morphogenic protein, they can support really nice bone regeneration. So to conclude, so these composite, they can have highly tunable mechanical properties, and also they can load and release bioactive molecules, and also they can be 3D printed, and they can support the osteogenesis. And then we're using these polymer for the osteochondral repair. So as we have already mentioned, these materials, they are injectable. So in this case, we can use them as an injectable adhesive for the osteochondral regeneration. So here shows you the osteochondral the structure. So on the for the bone part, we have something mechanically stronger, and also for the cartilage part, we have like something mechanically like slightly weaker. So we use the composite, so the polymer plus hydroxyapatite to regenerate the bone, and also use the polymer itself to regenerate the cartilage. So here shows you the schematic of the our project. So what we do is like this one is the our polymer plus the hydroxyapatite and also plus the bone morphogenic protein 2. So we inject them to the bone layer to regenerate the bone. And then we also inject these polymer encapsulating the TGF beta. So this is growth factor to help the chondral regenesis to regenerate the cartilage. And also one thing, and then after we inject them, and then we use the UV to crosslink them. So first of all, because UV, they can crosslink the materials itself, and also because for the both layer, we have the C1C, and these materials, they the bilayer scaffolds, they can have really like tight bonding due to the presence of the C1C. And also because the upper layer, they're soft, and also they have the TGF beta 1, so these can help the chondrogenesis. And also the bottom layer, they're stiffer, and also they have the BMP2, so these will help the osteogenesis. So these are some data. So from this one, we can see that our materials, they can, so this is the polymer, and this is the composite. And outside here is the water. So we can see that we can actually inject the materials in the water environment. This is something very good. For example, if we have the osteochondral defect, this means that our materials can be injected to the defect and they won't spill out. And also we can see that after we crosslink, we can form these kind of tight layers. So it's by layers, they are tightly joined together. And then we use the examine the chondrogenesis. So again, we're using two markers. So and one is the suffering O, and the other one is else in blue. So we can see that our materials loading to TGF beta 1, they can enhance the chondrogenesis. And we also use the alkaline phosphatase and also alizarin red to examine the osteogenesis of the composite. And we can also see that our materials loading the BMP2, they can support and also they can enhance the osteogenesis. And then we inject these materials into the rabbit female condyle. And we see that after implantation for about 12 weeks, we can form these, the cartilage can be nicely regenerated. And then we use the micro CT to examine the bone regeneration. And we can see that also when our materials, they are loading the growth factors, they can have a really nice formation of the bone. And then we slice these sections. We use the histology to examine the different sections. And we can see that these color, so for the here, this is the cartilage, and here, this is the cartilage. And we can also see that our composite materials loading the growth factors, they can have nicely regenerated osteochondral area. So this means that to conclude, so our materials, they can be cross-linked underwater, and also they can form these tight bilayers. So after the cross-linking, and also they can help regenerate both the cartilage and also the bone. And also by taking advantage of the photocrosslinkable polymers, so they're initially liquid, and then after solidification or photocrosslinking, we can make them this kind of solidified polymer layer. So we made them the micro pattern scaffold as artificial periosteum. So the reason why we want to have the periosteum is because if you just use, for example, the bone implant, so the bone regeneration effect may not be that ideal. And also the periosteum, they can help to recruit the blood cells. These will also help the bone regeneration. So this shows the what's currently available out there. So we have the cell sheet, acellular dermis, and also the porcine intestinal submucosa, and also the hydrogels. But these materials, they are either lack of the structure of the natural periosteum, and also they're usually mechanically very weak. So in this case, we want to develop a genus periosteum with the similar structure and function of the natural periosteum. So again, what we do is that we're using these polymer materials and we put them into defined patterns. So on the one side, we have these polymer side with a lot of brushes. So these will actually increase the interaction of this periosteum to the surrounding bone tissue, and then this will increase the tissue adhesion. And also we put the polydopamine on top of these brushes. So these will further make these materials more adhesive to the tissue. And on the other side, we're making these cell fine patterns. So these fine patterns will make the cell better aligned, and we can actually achieve both the angiogenesis and osteogenesis at the same time. So this is just some data showing that we have successfully synthesized the polymer and also the polydopamine. And this is how we make these kind of this made of this genus periosteum. So we can have a fine pattern mold, and then we put the liquid polymer in there, and then after the UV cross-linking, we have the solidifying genus periosteum, and then we coat the materials in the polydopamine solution, and then eventually we are going to have the adhesive genus periosteum. So we can see that on one side we have these fine patterns, and on the other side we have a lot of these brushes. And we can also see that, so this is the periosteum, and this is bone. We can also see that these materials, they can adhere really well to the bone. And then we examine the cytocompatibility of the materials. We can see that, so most of these cells, when they sit on top of both the polymer and also the polymer plus the polydopamine, the cells can survive. And also when we are adding the high concentration of the polydopamine, they can have better cell adhesion. And then all the materials, they can support these cells proliferation. And then we examine the effect of these fine patterns on the mesenchymal stem cells. So we can see that when we are having these very fine patterns, so the cells can better align, and then we can have increased ALP and OCN. These are osteogenesis marker. So we are going to have increased osteogenesis marker expression. And we also see that how the fine patterns can regulate this behavior of the endothelial cells. And we can also see that when we are having these fine patterns, so they can regulate the also the cell alignment, and then they can have increased VEGF-A and also nitric oxide synthase, this expression. So that means that they can actually enhance, when the fine patterns are really fine, they can enhance the angiogenesis. So after we confirm this, we apply the periosteum to the rat cavarial defect model. So we can see that when we are having these fine patterns and also the brushes with the polydopamine, we can have the optimum bone regeneration. And we also see that how these things affect the angiogenesis. So these red circles, they indicate the blood vessels. So we can also see that when we are having these fine patterns, and also the brushes and also the polydopamine, we can enhance the angiogenesis. So this is to show that, so these polymer, we can fabricate a sophisticated structure, so they can regulate cell fate, and then they can support the angiogenesis and osteogenesis. And also we make another fine pattern scaffolds for angiogenesis. So in this case, what we do is we mimic the structure of the leaf vein. And the reason why we want to mimic the structure of the leaf vein is because leaf vein itself is to transport the nutrition, like blood vessels. So for these projects, so we have this leaf vein mold, and then we put the materials on top of these patterns, and then we solidify them. So we can have this membrane with these leaf veins. So this is you can see that this is how these materials looks like. And then we see the endothelial cells into these the fine patterns. So we can see that when we have this kind of leaf vein structure, so the cells can be more pointed and they can migrate faster. And also we can see that, and then we apply these fine pattern membrane into the red cavarial defect model. So we can also see that, so our membrane with the leaf vein structures, they can support more these angiogenesis. You can see the circles here. And also we examine the function of the blood vessels, the newly formed blood vessels. So if we see these brown dots, that means that the blood vessels are leaky. So we can also see that the blood vessels generated using our leaf vein membrane. So we don't have these kind of proteins leaking out. So that means that the regenerated blood vessels are more intact and mature. So this again shows that the polymer, we can generate this sophisticated structure on top of that, and we can use that to regulate the cell fate. And also we are using there are many other applications of the photocrosslinkable polymer. For example, we can make them into the microneedles, and also we can make them into the bone screw, and also because we can regulate the viscosity of the materials, we can use them as a sprayable wound patch. And also we are making them as a cardiac patch as well. This is my lab, and also I would like to thank my students and also the funding resources who support our research. And without my students and also this funding, so we won't be able to do such good research. And this is Hong Kong, and welcome to Hong Kong, and welcome to PolyU.
All right. Thank you so much for Professor Shin Zhao. A very interesting talk on the photocrosslinkable polymers that can be used for produce the tissue regeneration. I would like to introduce the last speaker of the day. Okay. She's from her name is Professor Judith Su. Professor Su, she's assistant professor in biomedical engineering and assistant professor in optical sciences at the University of Arizona. She obtained her bachelor and master degree from MIT and her PhD from Caltech in biochemistry and molecular biophysics. She has a background in sensing, imaging, microfabrication, optical instrument. Again, and she has won so many prestigious awards. She actually gave many keynote speaker, including the Photocrosslinkable West, which I am a chair actually, and she has become a general chair of OSA in 2023 in Advanced Photonics Congress. I would like to give the floor to her.
Well, thank you very much for the nice introduction, and I'm very happy to be here today to present my work to all of you. And so my work is a little bit different than the previous two speakers. My lab mainly focuses on sensors. So I like to say we sense anything that's worth sensing. So we specifically specialize in ultra-sensitive sensors. So we look at things like environmental monitoring, translational medicine, so detection of low concentrations of biomarkers. And we're also interested in fundamental science. So we have projects on the basics of taste and olfaction. And this picture on the left is supposed to symbolize the peace and tranquility that we hope our sensors can bring for things such as environmental monitoring. Okay, so I first wanted to say that I'm currently hiring PhD students, so please come join us. This is actually taken from the window of my house, and you can see these wildcats, which are actually the mascot of the University of Arizona. So this is just the outline for my talk. So the main sensing platform that we use are called these whispering gallery mode microresonators. So we specifically focus on a toroidal configuration, and I'll show you a picture of that and explain what that is. And so first we do a lot of analysis of that. So we do noise analysis so that our sensors get the best signal to noise ratio. We do some flow analysis. These are simulations using COMSOL multiphysics just so that we can optimize transport of the analyte to our sensor for higher sensitivity. And then we target a wide variety of biomedical applications. So we look at cancer biomarker detection. We look at biomarkers for Alzheimer's disease. We look at drug screening for COVID-19. We have projects on understanding the basics of human taste. We look at things like performance enhancing drug detection. And then we have a large project on chemical threat sensing, so chemical warfare agent detection. And then another half of my group is on further improving our platform. So we focus on a bunch of applications, but then we're also focused on how do we make our sensor, better, more portable, more robust, higher sensitivity, et cetera, and giving it new capabilities. So our sensors, as I mentioned, they're called whispering gallery mode optical resonators, and this is named after the acoustic whispering gallery. So probably the most famous example of this is underneath St. Paul's Cathedral in London. So underneath the dome of St. Paul's Cathedral in London, there's a gallery called the Whispering Gallery. And if you whisper at one end of the gallery, your friend can hear you about 100 feet away because the sound goes along the edges of the wall with low loss. And so this is an example of, I was in Beijing many years ago. This is me in the front, my husband in the back, and this is the echo wall of the Temple of Heaven. And so you can see this curved wall, so he could hear what I'm saying even though he's in the back because sound is traveling along the edges of the wall. And this was first described by Lord Rayleigh, but I like to use the example of the Temple of Heaven because that was actually 400 years before Lord Rayleigh. And so our sensors are the optical analog of this. So instead of sound going along the edges of an architectural feature, you have light that's basically trapped within a glass device. Okay, so this is a rendering of what our sensors look like. This is called a microtoroid optical resonator. And then there's a simulation on the right. And so essentially what happens is that light is confined within these devices using total internal reflection. So as you sort of see from the animation on the right, you can evanescently couple light in using a waveguide or optical fiber. And then at a particular frequency known as the resonance frequency, you get constructive amplification of light within this device. So you can see light is going through this waveguide, and then you see this enhancement of light that goes around the ring. So light is continuously, totally internally reflecting around the rim of this, just like how light travels through an optical fiber, but light is not perfectly confined within the optical fiber. You have this evanescent field that extends outward about 100 nanometers, and this is what's called our sensing region. So this rim is sensing region. These bright colors represent the electric field within our sensor, and then as molecules of interest enter the evanescent field, the light continuously interacts with it over and over again, and this is what gives our sensor this high signal to noise ratio. And this constructive interference happens at this resonance condition, which is when your circumference is equal to an integer number times the frequency of light. And you can see that the amount your resonance frequency will change is proportional to things like your particle volume, your E field intensity. So why do we use microtoroid optical resonators for biosensing? One is that they have a potential for high throughput measurements because you can make them on chip. So here, this is an SEM of what the toroid looks like. So you can see they're about 100 microns in diameter. This pedestal is made of silicon, and this ring part is silica, which is glass, which makes it easy to be functionalized. And then these three circles on the bottom are the top view. So you can see that ideally you might want to functionalize each one with a different, capture agent, so antibody, complementary stranded DNA, and then you can look at things like panels of bio. It's a small sensor, so your sample volume required is less than 10 microliters. So I'm going to show you some work in which we detected things from just 1 microliter of a sample from a mouse. So This is really important if you have samples that are precious, hard to get. We can get real-time measurements of binding kinetics. So there are other techniques that can do single molecule detection, but in addition to detection, we can measure binding kinetics, which is going to be important for things when we look at drug screening. So we're looking at the affinity of different drugs binding. So we're highly sensitive down to single macromolecules, and we're labeled free. So that means we don't have to label what we're trying to detect. So we don't have to use a fluorescent tag, radioactive label. We can just detect things in their native state, which is quite useful because, for example, when we're looking at small molecule drug discovery, for example, it's not always possible to tag those drugs. So our advance is called, this is something we call FLOWER, which stands for Frequency Locked Optical Whispering Evanescent Resonator. So typically the way these measurements are done is you have a tunable laser and it scans through a variety of wavelengths in order to locate what is the resonance frequency of this cavity. And then you have a photodetector that detects this drop in the transmission of light that goes through your optical fiber. So you have your laser, it's tuning through a variety of wavelengths, and then you have your photodetector, and then at your resonance frequency or wavelength, you see a drop in the transmission of the light that goes through the fiber because the light is entering the cavity. So you can see this on the right. So this is what you're monitoring is the transmission through the optical fiber. You see this dip in your signal, this transmission dip, and then this is what you're monitoring as things bind. And so instead of scanning through a variety of wavelengths, what we do is we lock the frequency of our laser to the resonance frequency of our cavity. And then as particles bind and shift our cavity frequency, we measure the amount of voltage our laser controller has to apply to follow that event. And so this enables us to do real-time tracking. So instead of doing this comparatively slow scan, because instead of scanning and finding resonance, we're just locked to that resonance frequency. And this enables us to look at smaller and more transient events. And it also permits more averaging of our data. So this is our 3D experimental schematic. So you can see our toric, you can see your optical fiber. This is the top view. So this is what we use to evanescently couple light into our cavity. These red and blue balls are just a schematic representing nanoparticles. And then this schematic in the middle, it just shows us our active tracking of our resonance. So this is the transmission dip through the optical fiber. This is the response from our sensor that we're measuring. You can see that as the resonance shifts to a new location, we measure the amount the laser shifts on resonance. And then we have a syringe pump that we use to pump any sort of biomarker containing solution. So these are not sensors that are inside your body yet in this formulation. So this is on an optical table, and we take sort of biomarker containing solution and we flow it over our sensor. And this is just a video showing the transport of solution to our sensors, just so you can observe how quickly this process occurs. You can see that this occurs fairly quickly within seconds. So the toroids, this is a top view of the chip. This underneath this Roman numeral 8, you see these little tiny circles. This is the toroid. And so you can see that things can reach our sensors quite quickly, which is important when you're doing things like medical diagnostics, particularly things like infectious disease detection, where you want to get a very quick response. So we did some fluidic modeling of this. So you can see these are simulations, and the top part was experimental data. You can see we can replicate this sort of swirl effect quite accurately. What we modeled was we wanted to know how long does it take for things to bind to our toroids. So this is actually comprised of two parts. One is how quickly can you deliver analyte to your sensor, which makes sense. And then the second part of this is once your analyte has been delivered to the surface of your sensor, how long does it take to collide with your sensor and bind? And so we were able to get good agreement between simulation and experiment and get very, very quick detection within seconds, actually. And why this was important was when these sensors first came out, there was some debate in the field as to, these are rather small sensors. If you're relying on diffusion alone, shouldn't it take a very, very long time, like hours or days, for analyte to reach the surface of the sensor? But our simulations show that actually our sensors, because they're microsensors, are on the order of 100 microns, and they're not nanosensors like nanotubes or nanowires, we can actually get detection quite quickly, which I believe is a great advantage of our system. So this is a block diagram of flowers. So you have your laser, you split your light between the toroid which is shown as this red circle, and this auto balance photodetector, which essentially subtracts the signal from your laser with the light that goes through your toroid to essentially minimize any fluctuations in signal due to laser intensity variations. And then you're sent to this digital laser locking module. So basically you multiply your signal that comes out of your photodetector with a small dither signal, which is this 2 kilohertz or whatever frequency you want to use, sinusoidal waveform, and then this generates an error signal, which tells you how far you are off resonance. Are you on resonance? How far? If you're not on resonance, how far are you off? And then this is sent to a PID, proportional integral derivative controller, so that you can minimize your error signal and reach your set point as quickly and accurately as possible. And so the advantages of this, again, is that one, it continuously stays on resonance instead of slowly scanning past resonance. And then you can also sample more points per second, which permits more averaging of your data. We did a lot of computational modeling of flower. So you can see this is what we did in Simulink and MATLAB. So you can see your resonance dip. This is what the error signal looks like. And then we did things like, for example, as the quality factor, which is related to the photon lifetime of your cavity, as it increases, what is, for example, the optimal dither amplitude to multiply your signal with to get the best signal to noise ratio. So you can, this is this graph on the right. This is simulated data. So you can see we have this random particle binding, and what can we pick out? So this was our first application that we did. We were the first group to do single exosome detection. So exosomes are these nanovesicles that are mainly very difficult to detect because they're mainly filled with water. So the index of refraction contrast between it and its environment is very low. And people are very interested in exosomes because they're tumor biomarkers. So these are little bits of your cell membrane, and they're shed by all your cells. But in particular, when they're shed by tumors, they carry a little bit of the tumor into your bloodstream. And so if you can sample the blood, you can detect, is a tumor present and how far it's progressed without having to find or access the tumor. This is called the liquid biopsy. And what is one reason why exosomes have attracted a lot of interest. And so the black is our raw data. It has our 2 kilohertz dither signal imposed. And the reason we can detect these exosomes is because we functionalize the surface of our cavity with antibodies that can detect proteins that are present on the surface of these exosomes. And then what we do is we remove known sources of noise, and then the pink color is our final filter data. So you can see the voltage is, we can relate that to our wavelength. So you start out at one particular voltage or one particular resonance wavelength of your cavity. And then as an exosome binds, it shifts the wavelength, and then so on and so forth, which creates this staircase-like graph. And these bursts of signal that you see at around 2 seconds or around 4 seconds are what I term incomplete binding events. So it's where an exosome has entered the evanescent field of your cavity, it's trying to bind, but then it can't quite bind, and then it eventually binds. And then we do a low-pass filter on our data. So in addition to doing these noise reduction techniques, we also do filtering to better enhance our signal. And so this is our relationship between theory and experiment. The solid lines are theoretical predictions, as related to what we call a dielectric factor D, which is this parameter on the right, which is just essentially a combination of the index of refraction of your environment and the index of refraction of your particle. And so you can see that we have this agreement between, so the black is polystyrene beads, the blue is silica, the green is protein, and then the exosomes. At that time, we didn't know what the index of refraction of an exosome was, so we put it separately, although now we do know what the index of refraction of an exosome is. And so you can see that we agree with theory over a wide range of sizes and different materials. So cancer detection. So we then took this to mice. So we had mice that were implanted with human tumor mesenchymal, human Burkitt's tumor lymphoma cells, and which is a very aggressive tumor. And as the tumor grew in the mouse each week, we took blood from the tail vein of the mouse and we froze it down. And then we flowed our sample, the serum sample, we flowed it over the surface of our sensor, which was functionalized with antibodies, so that we could see, can we track tumor progression by the binding of these exosomes to the surface of our sensor. So this is week 0 to week 5. At week 5, the tumor grew so large we had to euthanize the mouse. And as you can see, at week 0, you see relatively low signal from our sensor, and then as each subsequent week progresses, you see larger and larger signal on our sensor, presumably as more and more of these exosomes are binding to the surface of our sensor. And then the control experiment, of course, is a mouse with no tumor, that you don't see the same increase in signal from week 1 to week 5. And then if you individually zoom in to each of these weekly binding curves, you can see these discrete changes in signal, these little staircase-like events, and then you can form a histogram, which we interpret as the binding of individual exosomes to our surface of our sensor. And we were able to actually pull out a size from this individual height, this step amplitude, and it corresponded with an independent measurement using field flow fractionation, which is a technique to size separate out particles based on an electric field. So this was our next work that we did on ovarian cancer. So ovarian cancer is the 5th leading cause of cancer-related deaths among women, and there haven't been good biomarkers for ovarian cancer. So typically, it may be detected when it's stage 4, it's very late, and there's high chance of a bad outcome. And so we have a collaborator, and her concept was to repurpose the Pap smear. So Pap smears are something that women routinely undergo, and DNA from ovarian cancers have recently been found to be detected from standard Pap smears. So that indicates that some tumor cell or some cellular debris is escaping from the ovaries for detection purposes. And so she had the idea of, for example, taking human tampon samples from people with ovarian cancer, dissolving the tampon, getting these proteins and looking at it and analyzing it using mass spectroscopy to see what these different protein levels are. So what proteins are upregulated in the patients with cancer and what proteins are downregulated, and to search for biomarkers. So her concept was to discover biomarkers using mass spectroscopy. So she first started with mice. So she took ovarian cancer cells, she injected them in mice, and she did mass spec to identify what proteins are upregulated, downregulated, and then she did proteomics to identify what those proteins actually were. So she also did imaging to show that this tumor burden would increase. And then the idea is once she discovers what these biomarkers are, she tells us what the biomarkers are, she sends us the samples, and then we see if we can detect these samples, like these biomarkers, at very, very low concentrations. So the idea is that you would want to be able to detect diseases very early, before physical presentation of symptoms, so that you can essentially save lives. So this is just a picture of the healthy ovaries, very cancerous looking ovaries. You can see that over time the tumor burden increases in this mouse model. And then this is her upregulated protein. So the way you interpret this graph is this chart is you see week 7 versus week 1. So there are 19 proteins upregulated in week 7 versus week 1. Week 6 versus week 1, 42 proteins upregulated, and so on and so forth. So she can see what things are upregulated. So she, in comparison, this is the mass spectroscopy signal, so she gets this intensity. And then the reason why she can't do detection using the mass spec is because she gets this intensity. She can't get actual concentration values, and the mass spec doesn't have the sensitivity our sensor has. So you can see that you see this increase in signal from week 1 to week 7. So then she gave us our biomarker. So what we started was we took our toroid, we functionalized it with antibodies for this known biomarker. This biomarker was called cystatin A. So this work is under revision right now. And then we first just did it in pure solution. Can we detect this biomarker? So you can see as each concentration increases, you get this increasing signal from our sensor, and then we also confirmed that it was present on our sensor using fluorescence. And then this is from the actual mice sample. So this was done in less than, so she gave us samples that were between 1 to 4 microliters of a vaginal lavage from a mouse. And so this would be too small to do on a traditional sensing assay like ELISA, for example. And the way you interpret the signal, so this flat region is buffer, then you flow in your sample, and then this large spike in signal is called the regeneration buffer. So this is a regeneration buffer that's used to remove things from the surface of our sensor. And then if you just focus on the S part, which is our sample, we can compile this, from day 0 all the way to day 56, and we can track this progression of the tumor. And then we can calibrate and we can see what is around, what concentration is this present in the mice. So in this case, the student injected a known concentration into her sample and saw this dashed horizontal line is around 100 picomolars. And then you combine this with flour and mass spec, and you get this. You see that the trends correlate between what we get from flour from 5 different mice and what they get with mass spectroscopy. And then we've since done this with human tampon samples as well, though I don't have that data right here in these slides. So the next thing we did was Alzheimer's detection. So A-beta 42 is a biomarker for Alzheimer's disease. So you can see that in people with Alzheimer's, you get this accumulation of these amyloid beta plaques in your brain. So you get this positive scan, you see a lot of this amyloid beta. And so typically the way people detect Alzheimer's is you do a cerebrospinal tap, which is very invasive and very painful and has low compliance. And so what people have started to do now is doing a blood-based assay for Alzheimer's. So the idea is we have a very sensitive sensor, and some of these proteins might leak through the blood-brain barrier into your bloodstream, and that if you had a very sensitive sensor, you could detect this at a very early stage. And although there's currently no cure for Alzheimer's, other medical groups are currently working on ways to treat Alzheimer's. And so an ultrasensitive detection method of these biomarkers is rather important. So the current comparison is ELISA, so it has high throughput. It's these 96 well plates, if you guys have ever seen it. So it's basically a dual antibody assay. You have an antibody, it binds your biomarker, you have a secondary antibody, and that has, for example, like a fluorescent tag or an enzymatic label, and it's essentially this colorimetric assay. And then but there's several issues with ELISA. One is it takes a very long time. 2, it has something called hemoglobin contamination. So if the samples that you get from your physician have hemoglobin contamination, they essentially have to remove those samples. And then you get significant variation in results between labs. So even same sample, different labs, because it requires a trained person to do it, you can get significant variation in results. And even kits from different companies can give you significant variation in results. So we first did this detection of this amyloid beta in pure solution. We were able to get down to 500 nanomolars, which was 3 orders of magnitude lower than the current ELISA limit of detection. And then when we did a different sort of surface functionalization technique using a lipid bilayer, we were able to decrease that down to 100 nanomolar. And then here we're doing amyloid beta screening in cerebrospinal fluid patient samples. So we have 3 patient groups from people who are healthy, people with mild cognitive impairment, and people with full-blown Alzheimer's. This is diagnosed through behavioral assessment tests, and we can distinguish between these 3 patient groups. And now the students are working on doing this in the blood samples. So I'll just quickly go through. So we're doing some drug screening. So this is a project that we're doing in collaboration with Bill Goddard's computational chemistry group at Caltech. So we're screening for drugs to bind for COVID-19. So he does a computational screen of FDA-approved drugs to look for things that can interfere with the binding of the SARS-CoV-2 virus with the ACE2 receptors in your lung. So the first thing that we did was, can we get accurate binding affinities with our sensor? And so the answer is yes. So the way you interpret this graph rate is you see this wavelength shift, and then it increases for higher and higher concentrations. And then what we can do is we can take the equilibrium wavelength value, we can get a binding curve, and from there we can pull out the binding affinity of various things. So the first thing we did was we looked at the binding affinity of the receptor binding domain of the SARS-CoV-2 virus, which we refer to as the spike RBD, to the ACE2 receptors in your lungs, and we were able to pull out binding affinities that match with literature. So it actually varies depending on what buffer you use. So this is tricing buffer, and we also did PBS. And what we did in PBS matched with literature. There aren't other people who did this in tricing buffer. And then what we did was we looked at different drugs that he found. We looked at the alpha, delta, and omicron. So first we looked at alpha, delta, and omicron binding to surface Mortorian. We pulled out the binding affinities of this. This is just to see if our sensor gives the correct values, which it does. And then we looked at this, then we do this inhibition curve. So what we do is we mix in our drug with our SARS-CoV-2 receptor binding domain, and then we look at the different concentration of the drug and see how much that inhibits the binding. And then we also are interested in looking at understanding human taste. So we're looking at basics of human taste. So the idea is that you have bitter taste receptors in your mouth, but they're also present throughout your entire body, not just in your mouth. and they're associated with a variety of diseases, and there aren't X-ray crystal structures of these. And so this group that we collaborate with, we do a lot of collaborators projects, predicts the 3D structure of this and how it binds to various drugs, and then we test this out on our sensor. I think in the interest of time, I'll sense we had a project on performance enhancing drug detection, but and then I think I'll very quickly talk about our project on chemical threat sensing. And so previously I've been talking about biological sensing. Now we're doing chemical sensing in air. And so we don't use antibodies, but what we use custom synthesized polymer coatings. And so the idea is that as target gases, chemical warfare agents diffuse into your polymer coating, it causes a change in refractive index and a swelling of the polymer layer, which causes a change in your microcavity resonance frequency. And so here we're doing part per trillion trace gas detection. We're looking at things like toxic industrial chemicals like formaldehyde, ammonia, chemical warfare agent surrogates. So we get shifts to longer wavelengths in reaction to DIMP, which is a sarin surrogate. And then we also get very good selectivity of our gases. And so this is actually better performance than anything out there, with the exception of graphene, pristine graphene, which they do their experiments in vacuum, and they don't have the selectivity from these different coatings. And it's certainly better than any other whispering gallery mode gas sensor that's out. Okay. And then we've also done work using multi-target sensing. So this is where we have interest in, for example, just a sensor that can tell you is something dangerous present in the room. So this would be a low-cost sensor that tells you, is it safe to enter the room, for example. So what we did was we do a mixture of these polymer coatings, we put them on the toroid, and then we can still get very good trace detection using mixtures of polymers on the surface of our sensor. And then finally, the last thing I'm going to talk about is we've been trying to incorporate other features into our sensor. So right now we can detect things. So we functionalize our sensor with an antibody polymer coating, and then we look at the change in resonance frequency as things bind to the surface of our toroid. But what we're interested in is, can we get detection and identification without having to do that? Because what we do now requires that we know in advance what we're detecting. And so what we want to do is we want to incorporate frequency comb spectroscopy into our detection. And so here we've published this work where we've generated a frequency comb in water at this near infrared wavelength. And we use what's called an avoided mode crossing and approach, so that we don't have to do this dispersion engineering of our cavity. So we don't have to engineer the cavity, we don't have to engineer the material. We can just use our toroidal biosensor, which we've already shown has been capable of very high sensitivity biosensing. And based on this, we can generate a frequency comb in water. And so right now we're working on generating a very, very broadband comb in water, such that we can do simultaneous absorption spectroscopy, look at the attenuation of these comb lines, as well as detection, looking at the shifting of these. And then we also do work on these hybrid plasmonic devices. People have coupled these devices with plasmonic devices because these, like for example, these gold nanorods can generate these sensing hotspots at the ends of these nanorods. And what we've done is we've generated these, through simulation, these trimeric structures, which we call these dark mode plasmonic structures. And what's interesting about these is that they're robust to orientation changes, and that they can give you your intensity enhancement, then you have minimal Q degradation because you're reducing scattering. And then we've been looking at these alternative robust light coupling strategies. So we've actually been experimentally implementing this, where we use high-speed optical tweezers to put these nanorod gratings on the surface of the toroid, so that we can get ultra-high Q cavities on chip through free space coupling, and we don't have to deal with environmental disturbances from like the taper moving against the toroid, which can cause noise in our signal. So I'd like to thank all my sources of funding, my lab, and happy to answer any questions in the panel conversation now. And I thank you very much for your attention.
Thank you very much, Judith. Yeah, I like the talk about microresonance. Actually, my professor actually in UC Berkeley actually did this work before. So Ming Wu, I'm not sure he's doing it. So I'm quite familiar with the technology actually. Yeah, I will ask you tough question. Okay, be careful. Yeah. Anyhow, so the floor, the session is open for question, and I like to hear from the audience first. If you have any question.
Okay, yeah, maybe I go first. Okay, I really interested in this talk, and I think a lot of questions here. Okay, first, maybe my question was go to Sassy. So, Sassy, you are really smart. Use a natural rubber to print it, and this was quite easy and company. I mean, 2 or 3 years ago, I heard a talk from Professor Cun Jiangyu, who is doing for the rubber electronics. Okay, so did you read his paper? I think you must be interested. Yeah. So for this, I mean, you printed all this kind of natural rubber composite. Did you think about how to use it for more function?
Yeah, that's a very good question, Alice. Thank you. More function, yes. Actually, we are now proposing another function into other material that we are making, and even though it's not really a composite that we're looking for, but we could adjust some properties of the material so that it can be used to simulate how the ultrasound picture would be like for the medical doctor, so that we can use it as a training model for the medical doctor to practice using an ultrasound probe along with some kind of needles or other kind of medical equipment, so that it could more accurately diagnose the symptom of the patient. For example, the cancer in the breast cancer.
Okay, great. Maybe a follow-up question. Is this very easy to control for the biodegradable, right? Yeah, but we use this bit.
Biodegradable.
Yeah.
Yeah, natural rubber is biodegradable.
I mean, it can be controlled for the time, for the duration of this.
I see. That's very interesting. Well, we haven't looked into that yet. But I'm pretty sure we can tailor the time of the degradation because, there are some type of modification to the molecule of the natural rubber. We call it grafting, and that's how you adjust how it decomposes. So that's one way that we can use to adjust the time for the degradation. But no, we haven't studied further into that, and that's a very interesting discussion. So maybe next I'll go to my lab and then propose this question to my colleagues. Thank you.
Okay, very, very nice. Yeah. Actually, I'm thinking, and the first, I can use tags. We have a discuss about this, for why we want to invite all the scientists from different part of the world. Because I think, different part of the world, they have a different kind of resource. They are thinking different. They can use all this kind of resource, either natural resource, right, or human resource to do something new. Like this time you point out for the natural robots, that's very important because everywhere have so many kind of, so many materials we can use. Use our brains, so we can come out a lot of ideas. I love that. I think you can inspire a lot of people, try to use all these natural materials to their research. Okay. So, Weibo, I have another question, so then I come back to you. Okay. I have another question is for Xin. Yeah. Xin Zhao, Professor Xin, you really have done, very inspiring work in several fields. So maybe my question is out of your field because I don't know more about, the biotissues or these issues. But I'm thinking you make for the artificial bones, right? These tissues, these kind of structures. Is when they implant in the body, is that possible to they use this, a kind of artificial agents or organs like a tongue, for the drug delivery? Is that possible? We put.
Oh yeah. So one thing, Yeah, I mean, usually like people will load drugs in the in the material. So one advantage of my materials is like, because when they cross-link, so when we make them like from liquid to solid, they don't generate a lot of heat. So these will make the encapsulation of the bioactive molecules possible. So bioactive molecules is what we consider as a drug. So they can be used to release the drugs.
Okay, that's very
Yeah,
nice.
so and like
This
yeah, and also we so when we talk about, so this is very unique advantages of the our materials. But like in general, if you just want to release some very small molecule and very stable drug, so other polymers, they can also do the job. So ours is just like they have unique advantage is to release, encapsulate, and also release the bioactive drugs like growth factors.
Okay, how nice. If yeah, we can use this way. I think they will save a lot of kind of patients, their time, because they
Yeah.
always think about every day what time, yeah, to get the drugs, to do all these things. If automatically, can be released from.
Yeah, so this one we actually when we do the animal study, we actually compare our scaffolds, so how fast they can regenerate bone, and also compare them with the commercial products. And we can actually do like twice, so basically generate bone faster than the commercial products. So this is something very good, is because, for example, in this case, if our patients, they will be hospitalized for less time. So this is also very good. This is actually very good. So when we have less time staying in the hospital, this will reduce the cost of the whole thing.
Okay, very, very nice. Yeah, so I love this. Yeah. So Weibo, I give the most challenging question to you for Judith. Judith.
All right. So Judy, yeah. So to be fair, right, because she hasn't been asked yet. So actually, Judy, are you actually pushing for making the device which has very high Q? Because I know that the more the high Q, actually, the longer the period of that the light can store in that resonators. And what are the typical Q values that actually are shooting for, and there's some more room for improvements or not?
Yeah, so I think it depends on our application. So for our frequency comb application, we want to shoot for as high as possible. So we do like 10 to the 8. And so for there, we actually use toroids that are about 300 microns to half a millimeter, so like 500 microns, and this reduces our bending length so we can get higher Q. We're not trying to push beyond 10 to the 8, for example. For our biosensing experiments, we will do anything from like 10 to the 5th upwards is actually sufficient for our biosensing experiments.
I see. And so these devices need to be annealed as well, right? And what are typical gases you actually? Sorry, I'm not asking because I'm microfabricated, guys.
You said these have to be annealed. Is that what you asked?
Yeah, the annealing gas.
Well, we don't put them in a gas. What we do is how they're fabricated is it's a combination of photolithography and etching. So we pattern circles of photoresist, and then we do an HF etch, and then we do a dry xenon dichloride gas etch, and then the final step is this CO2 laser reflowing step, where we use the CO2 laser at 10.6 microns just to heat the structure, and then it melts, and then it collapses and forms this toroidal structure. But we don't have to do any sort of.
Anymore. Oh, okay. Oh, that's really interesting for me. Yeah, thank you. Alice, your turn. Or there's some.
Yeah. Okay, cool. Maybe I can follow up on another questions. Judy is like Weibo say he was good at that fabrication. That all these things. But when I see that round, structures in nanoscale, I was also very interested. Can you, fabricate like a big array?
Yes, we can fabricate a big array. So actually, what we do is we fabricate this on the wafer. And so what we do is we pattern many of these structures at once, just through, we have a photo mask and, just many different circles of different, whatever size we want. And then you just shine light through your photo mask. And then you can make these large arrays. The only part that we sort of essentially do by hand, but then we can also still make arrays, is this last part where we do the CO2 laser reflow, which is we create this structure which is called a microdisc, and then the final step to make it from a disc to a toroid is that we heat it and then it melts and it collapses. But then if we wanted to make large arrays, you could automate like the laser cutter to do this. So you can make large arrays. Yes.
Okay, it's very nice. Actually, I'm thinking, if you can issue me, I can use your pictures for this echo wall, yeah, in Beijing, that one. So I think it's a very good example for my teaching. I think the students can find, where is the high tech come out, where is the ideas, what's come out. Is from all these kind of interesting things.
Yes, I can send you that picture.
Okay, thank you very much. That's very, very nice pictures. Okay, yeah. So another comment is Judith. Yeah, when I listen to your talk, I reminded someone always tell me, Alice, when you give the talk, you speed like a machine gun. Yeah, really fast, Don't matter, they can follow up on that like this. So Judith, same thing, even, speedy than me. Yeah, I think I can give you a comment is the next time you will think about we, talk to, other people's maybe not mother language in English, maybe a little bit slow down. Yeah.
Okay. Yes.
Okay, Weibo, we still have some time for questions. Yeah.
Yeah, sure. I'd like to I have this question for Professor Shin. I'd like to know actually how stable are these photocrossing polymers that after you actually inject into the bones, are they there's no attacking from the immune system, they can get absorbed and then become part of the tissues of human body, or how does it work?
So these materials, because they have the lactide there, so they are actually degradable materials. And usually, if we implant them, they should be degraded from about 6 months to about 2 years. So they are actually slowly degrading.
Okay. Thank you.
Okay, Shin. Yeah, I have the same question. Is this degradable speed is controllable? Tuned by
Yeah.
use. Okay.
Yeah, so this is also the advantage of using the photocrosslinkable material. So because we say that we can control the cross-linking density, so you see these kind of grades. So if they are cross-linking density is higher, that means that they are more resistant to water. In this case, they degrade slower. So if the cross-linking density is lower, so they've got looser network. So in these cases, water is easier to come in and break those bonds. So in this case, they will degrade faster. So we can control the so by controlling this cross-linking density, we can control the degradation rate. And also, as you see the other application that slice, so we can make them for the bone regeneration. So we can make them very stiff, and we can also make them like for the for example the cardiac patch. We can also make them like soft and elastic as well. So we can control these the mechanical properties while controlling the M and N of the polymer.
Okay, nice. Yeah. So Weibo, can I ask a question for you? Your friend Sassy. Yeah, because normally, yeah. So this question you can answer, you cannot answer. Okay. Yeah. Normally, we met a lot of Thailand people. Yeah, we went to Thailand many, many times. So always the most beauties, Yeah. So actually, from my side, I'm thinking they are good at dancing and the artists and all these things. Yeah, so we never think about all these beauties are good at scientists. So, Cesar, is that possible? Can you tell us some story about your education? Yeah, how you get to this path? This path to be a scientist. Yeah, is that popular for the girls to choose this one in Thailand?
Well, actually, when I was a student, I was an engineering student, right? So it wasn't popular for a girl to be in a college of engineering at all. But I decided to do so anyways because I think that's where my passion is. Well, when I think back for all the toys or the books that I liked to read when I was little, it all addressed on the scientific side or the technological advances. Even even like the books that I read when I was little, it was still related to the scientists or the physicists in the past. So I think I made the right decision to like continue my career in science and engineering. And when you mentioned that, like the girls or the female, how would we fit into the careers that related to science? I think we also have the benefit over. I don't want to say over the male or the boys, but we have additional benefit. Um, it's like how we pay attention to details much better than other groups of the world. So I think with that you can be more creative with your scientific work, and you can observe some behavior. You can imagine further, and you can put stories together so that will be a new finding for your research and scientific work.
Okay, very great. Yeah, I like your answer. So I must give another tough job to Weibo. So I came to Thailand several times. Yeah, we even host some conference there. But this was my first time. Is my first time see the female scientist from Thailand. You, yeah, this is your first time recommend your female, colleagues. So be sure that you know more in the future. Okay.
Yes,
Yeah,
I
we
hope
know
so too.
many
Thank you,
years.
Alice.
Yeah, we know many years. I know WP many years. We host many international conference or events together. So, but always come out is the boys, right? Yeah, Weibo. Yeah, exactly. That's true. Yeah, Sassy is the first, female scientist I met.
Wow.
The
Yeah,
honor is
from
mine.
on the
Thank you.
stage, yeah, I'm sorry to say that, but I'm quite serious on this. I hope I can see more. Okay, yeah. Weibo, okay, take my words.
Okay, sure. Maybe I ask a following up question to Sasi. Actually, this is a big question. What was the biggest challenges to be the first in the world to actually print this natural rubber? I haven't heard it before. You explain to us in a little more details.
Sure. Thank you. Well, the biggest challenge would be is because nobody has done it before, and it's almost impossible for us to like go on Google or go on the find a publication or find some other evidence of why it didn't work. Most of the time, my experiment before I can invented the technology, it didn't work, and we don't know why. So but I think I'm lucky enough to overcome that challenge by having a good team, because we also have some people from like me from engineering, and we also have material scientists. We have some chemists, and when we combine our experience, our knowledge, our expertise, it could address all those challenges that we have in the lab. Because if it was just me, an engineer who was trying to make the natural rubber printable, I would never be able to do that because I don't know how it cross-links. I don't know how it works for the natural rubber. And when we have those like good team with a good balance of your expertise to work together, um, we can just make it happen and make it possible. And I think that's applied to most of the cases for our speakers here, as I could see from like how their work was based on the multidisciplinary research.
Thank you.
Okay, yeah, that's true. My first time here, 3 printing for the natural robots. Yeah, I think most of them fabricated in another way. So yeah, I mean, you mentioned that you have worked together with quite different peoples, right? Yeah, I think that's one benefit for the ladies, for the female scientists. So good at the communication. right? Yeah, we can easily, to get people working together. I think that's one benefit. Yeah. So yeah, for Judith, you are working in several kind of fields, so you have the students also from a different field too, right? Or you collaborate with them. So did you have any kind of comments or suggestions you can share with us how to get smooth for this kind of collaboration?
Oh, yeah. So I hire basically from all sorts of different fields. Actually, one of my best students is from Thailand. So if you have any students from Thailand, please send
Really?
please send them
Really?
to me.
Ouch. I'm
Yes.
surprised.
So so I guess in suggestions in terms of how to get the collaborations going, I think it's just to get out and meet people. So I'm hoping actually by giving the talk here, maybe this can spark some collaboration as people get to know me more. And then I guess as you naturally meet people, then you get to meet other people that they know, and people as they get to know your work, they have other ideas maybe that you didn't even think of yourself. So I guess the only advice I have in terms of that is just to try to have some visibility in your field through giving talks at places that other people in your field will go to and stuff like that. And yeah.
I'm thinking about maybe Thailand food work.
Yeah.
We are the
Okay.
hub of innovation. Please keep recruiting Thai students here. Thank you.
Good.
I would love
Yeah,
to have more Thai students.
Thank you.
that's nice. Yeah. So for Xin, yeah, I realize now you are in Boston, right? Yeah. So yeah, so you take sabbatical there, or you have some collaboration there?
Or I take sabbatical leave here, and also the last day is so the supervisor is when I was doing my postdoc.
Okay.
Oh wow, very good relation, huh?
Oh yeah, many years ago. So yeah,
May I ask one question about your photocrosslinkable polymers?
Mhm.
What are the next challenges that you would like to actually implement that you haven't been able to actually do yet? Maybe you can share us
Or
some
so
on.
so we are now still doing the different explore different applications for the materials. So one thing we really want to do that is that we really want to like get some kind of approval, like for example FDA, those kind of things. And also in China it's like the CDMA, those yeah. So we try to see if we can actually use that in clinic. So this is something like we are struggling now. It's like extremely difficult to get funding to support these kind of clinical trial. So so I think the biggest challenge for me is really like how we can make people believe and also get more confidence for the materials, and also we can kind of attract some funding to try do the clinical trial of the materials.
I see. Well, I
Yeah,
mean,
maybe collaboration with some medical doctors or something. Yeah.
Oh yeah, well, my publications is already with the medical doctors. I think the major thing is really like we are definitely need to collaborate more, and then to get support from like more like medical doctors, and also need to get the industry to believe that this really works and they can compete with the market, some other market materials. And also they would like to fund us. I think this is really like the biggest challenge now.
Okay, good. I think ICANX is a really good platform. Many audience, maybe heard about this will contact you possibly. Yeah, I
That'd be
hope.
great. Thank you.
Okay, cool. Yeah, we almost on time. I think we can run now.
So we have another 7 minutes. So you want to wrap up, or maybe I could ask Sasi one more question?
Yeah, for sure. If you ask questions. Yeah.
Okay. One of my last questions is that can this conductive rubber that you made sense any type of gases, and will the sensor be selective enough to identify type of gases?
Well, as of now, it depends on if that solvent or if that vapor is a good solvent for natural rubber, because I'm using how it's sensitive to solvent to be able to detect the vapor. But that was a very good question, because it can actually predict it. The sensitivity of the natural rubber can be predicted based on a value that will reflect how solvent affect the natural rubber. So that's one way we can predict. And for the selectivity, that's still a challenge for our research. So we're still working on that. And what we're trying to do is we're trying to modify the natural rubber so that we can make it less sensitive for some vapor and make it more sensitive for another one. And when we have an array of different types of rubber, and that's how you have different signals based on each one of these. And then when you combine the signal, it's more like an FTIR result that you can predict which peak is which vapor. So that's the future work that I'm looking forward to. But still, we need to include more people from, like the AI engineer or the coder to be able to achieve that. So I guess my team needs to be expanded further to be able to achieve the best selectivity for the sensor.
All right. Thank you so much. And that will be my last question.
Okay, good. Okay, I don't have further questions.
All right. I guess the whole session will come to an end now. I'd like to thank all the speakers here. I'm surrounded by beautiful scientists. Well, this is for the first time. Actually, I would love to meet you all in person, if possible, but virtually it's good enough for me, I guess. Well, surrounded by the stars of the scientists and engineers here. Hopefully we could invite you to come back to give some other talks on different topics. And Alice and I would like to thank you for coming to this virtual forum here.
Thank you for having us.
Okay. So WP, don't forget our certification.
Oh yeah, sure. So we of course as a tradition of ICANN, we would like to actually give you the certificate. Sorry, let me try to share my screen, which I don't know where it is now, but okay, let me.
So excited. Okay.
So excited, exactly. So I like to give the first certificate to Dr. Srisawadi Sriwadi, from National Materials Technology Center of Thailand. Thank you.
Thank you for having me.
And the next one, I'd like to give the certificate to Professor Shin Zhao from Hong Kong Polytechnic. Thank you. Thank you very much for coming. Oh, she's not here anymore, I guess. Oh,
yeah, I mailed.
Yeah, I'm here. Yeah, thank you.
Oh, yeah, all right. And the last certificate I'd like to give you, Professor Judith Su from the Arizona State, University of Arizona, Tucson, USA. Thank you very much for joining us.
And thanks for the opportunity to speak. Love to speak again.
All right, I think that's conclude our talk. And so for the next talk, we will have it on March 28th, next Tuesday. And these are the following speaker. Unfortunately, I could not read Chinese, but I'm guessing the talk will be in English. So I think everyone who are interested can join. Yeah. All right. And that's it. We will see you again next Tuesday.
Okay.
不再是奇迹， 不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。